Hey everybody, welcome back to another round of astronomy. And yeah, let's get going. Today we're going to spend a couple of minutes discussing what actually powers the interior of a star. And along with that, I guess you could say that we're going to discuss what distinguishes between a hot ball of gas in space and a star. So let's get going. So the first thing I thought we might discuss, or at least that we should overview, is how do you actually form a star? And if you will, what's the ingredient list for the universe in order to make a star? And the nice thing is that it's fairly simple. It's one cloud of gas. So to remind us of this, I have here the Eagle Nebula. This is a very famous image taken by the Hubble Space Telescope probably around 95, and then it was actually retaken again in 2015. And I think one of the cool things is that you can actually see a little bit of a change to the Eagle Nebula. This is a region of active star formation. We know that there are stars actually being formed in the interior of this cloud. And generally that's the case for pretty much a lot of stellar nebula that we see out there. So the ingredient list, one cloud of gas. The second thing that we should ask ourselves is how do stars, what is the energy source for getting a star to start forming? And you already know what that energy source is. So for example, let me remind you, let's say that I have 4 people on the Earth, and each person has a little blue racquetball in their hand. And if they were to each simultaneously let go of that racquetball, what would happen? Yeah. Each of the balls would fall towards the center of the Earth. Now we can apply the same idea with stellar nebula. It's just that the time that it takes for this to occur is dramatically longer. Okay? So instead of 4 people holding on to individual balls around the Earth, you could think of 4 hydrogen atoms surrounded or on the outside of this hydrogen cloud of gas. Now, as these atoms fall, they'll speed up, they'll have an increase in kinetic energy, and from our discussion about temperature, we know that if the individual molecules of an object are moving faster, on the microscopic scale, we interpret that on the macroscopic scale as being an increase in temperature. So the ingredient list, one cloud of gas, we give it millions, hundreds of millions, maybe even billions of years to gravitationally collapse. During that gravitational collapse, the temperature of the gas increases. Okay? So that's almost enough to get us to the right spot. Okay? There's another thing that we have to insert here in order to really get us a full-fledged star. Okay? You ready for it? So I like to refer to stars as being master alchemists. Now, if you're familiar with the term, alchemy was the branch of chemistry interested. Maybe I shouldn't say the branch of chemistry. I should say the precursor to chemistry. And alchemists were interested in transmuting one element into another. Generally, it was some element that was not very valuable and making it into something that is very valuable. Lead into gold, for example. Nowadays, we know that that's not something that's particularly possible in the general sense. You can't just take lead and do some chemical stuff and turn it into gold. Okay? Now that being said, there is a very interesting process by which we can take one element and turn it into another. You might be more familiar with the nuclear fission, that's where we get our nuclear power. We take a uranium atom and we fission it. We break it into constituent pieces, and when we do that, we release a little bit of stored nuclear potential energy. Okay. Now, we won't go into what does that mean. I mean, okay. So, but when we do that process, we actually change the uranium atom into something completely different. Okay? Stars also do this process, except rather than taking an atom and breaking it apart into different atoms, new different atoms, it takes two atoms and combines them together to form a new element. Okay? And when we do that, we don't call it fission, we call it fusion. So a star is a master alchemist, and it fuses, to begin with, 4 hydrogen atoms to form 1 helium atom, plus just a tiny bit of energy. Okay? Now, we can do this process here on Earth. Okay? Unfortunately, we can only do it in an uncontrolled reaction, a thermonuclear device. Okay? And it's called a hydrogen bomb, but it is doing the fusion process in order to generate the excess energy, and that's where you get the kaboom. Okay? The sun and every star is the exact same. It is an uncontrolled thermonuclear explosion, a hydrogen bomb going off in space. Okay? Of course, the nice thing is it's so far away we don't have to worry about all the nasty effects of it. And you might ask, well, why doesn't the star just explode? Why doesn't the star just disintegrate into nothing if it's this huge, powerful explosion process? And the issue is that the gravitational force of all the material of the star basically keeps it from blowing itself apart. So it's this cool balance of the nuclear fusion process trying to cause the star to blow up, and the gravitational forces keeping the star together. And it's that nice balance that actually causes it to be a sphere. Pretty cool, right? Okay, so let's go ahead and let's get a little deeper. Is there a way for us to quantify the amount of energy that's actually released during this process? And it's always interesting because if you actually take the mass of the 4 hydrogen atoms that you fuse together and you look at the mass of the helium atom that comes out, you'll find that those two masses don't actually equal each other. The mass, the material that you put in, doesn't actually equal the material that comes out. There's a slight difference. So let's go ahead and discuss that for a moment. So I'm willing to bet that before this class, or maybe even during this class, my guess is that if I asked you to name a physics equation, right, go ahead, think of a physics equation. You got it? Yeah. My guess is that if you stop 100 people on the street, 99 of them are going to tell you one of two equations. They're either going to say Newton's second law, F equals ma, or they're going to give you this other equation I'm thinking about, and I'm sure that some of you are thinking about as well. E equals mc squared. It seems like those are the two equations that pretty much everybody is aware of at some point. So here is a place where we'll actually use E equals mc squared. If we compare the mass of the hydrogen atoms that go into the fusion process, and we look at the mass of the helium atom that comes out, we'll find that there is a slight difference between those two masses. Okay? Now, where did that extra mass go? Where did that material go? Einstein was able to figure out that that missing material, that little piece of missing mass, is where the energy comes from. It is converted into pure energy. Now, because of that c squared, what we have is that a very small amount of converted mass can yield a lot of energy. And this process doesn't have to stop with just hydrogen. In fact, when we talk about the evolution of stars and the stellar death, we'll see that stars, first of all, go through their hydrogen fusion. But then, after that, they can fuse helium. So we'll see a helium fusion stage. And depending on how large the star is, you can keep going. You can get carbon, oxygen, silicon, iron. Okay? So it doesn't have to just stop with hydrogen. Okay? So let's get some practice with that. So here's a question for you. How much energy could be produced by converting 1 kilogram of material into pure energy via fusion? So taking 1 kilogram of material and turning it into pure energy. Go ahead, take a minute, hack it out. You got it? Yeah, good. So let's go ahead. I said, hey, 1 kilogram of mass. So we will place that in for the m in our equation. So we'll go ahead and put in the m. And then remember that the speed of light, we'll have to look up that, but it's 3 times 10 to the 8th meters per second. Now the other thing I should be careful of here and should highlight for you, remember we have a squared here. And so when we have a square, parentheses squared, we have to square everything inside the parentheses. So we have to do the 3, but we also have to do the 10 to the 8th. Okay? And so the final result, after we go through and do all of that, we get 9, 3 squared, times 10 to the 16th. 10 to the 8th times 10 to the 8th is 10 to the 16th. And so at the end of the day, we have 9 times 10 to the 16th joules of energy are produced just by converting that 1 kilogram of mass into pure energy. Now, that might not have very much of a sense. Like, where does that come from? So let me give you another idea here. Okay, for comparison, of course, this is an image of Clifty Falls Power Plant down by the river. And just for a comparison, the U.S. total production in 2019. Okay, so this is like 500 coal-fired power plants all over the United States, running 24 hours a day, 365 days a year. Okay, the annual production of everything total is about 10 to the 19th. Okay? In other words, if we could do this fusion process for 1,000 kilograms of material, we could power the United States for a year. Which is why, and I'll have some images, this is why this is an active area of research. Can we actually perform the fusion process in a controlled, confined manner? Because if we can, the benefits could be huge. Okay, so I've got another question for you, okay? So latch on to that. We'll take that number. We're going to put it to the side for a second. I've got another question for you. And where this question is leading to is, I want to start thinking about, can we get an estimate for how long the sun will be able to sustain the nuclear fusion process? Okay? So let's get at this. Okay? The apparent brightness of the sun is roughly 1,500 watts per meter squared as viewed from Earth. Okay? So that is how much energy the sun deposits on a square meter of Earth every second. Okay? So what is the luminosity of the sun? Go ahead, and I've given you the conversion 1 astronomical unit to meters. I've given you the brightness of the sun. Go ahead, find out the luminosity of the sun. You got it? Yeah, good. So let's go ahead and rearrange this so that the brightness is on everything, all the known stuff is on one side of the equation. The unknown is on the other side. And now I'm going to go ahead and substitute in numbers. We're given the brightness of 1,500 watts per meter squared. And we know the distance from the Earth is 1.5 times 10 to the 11th. So we'll go ahead and substitute that in. And again, we have an issue of a number in parentheses squared. So again, remember to square everything when you're putting it into your calculator. At the end of the day, we get a luminosity of 4.2 times 10 to the 26th watts. This is the total energy output of the sun every second. Okay? Watts is a joule per second, energy used per second. Same unit that you see on a light bulb. Okay? Okay, so here's the next question. Okay, now we're going to take those two numbers that we have, the last question answer and this question, okay? And we're going to use both of them. So here it is. The sun releases 4.2 times 10 to the 26 joules every second. So a joule per second is a watt. Okay? Question for you. By how much does the sun's mass change every second? And you say, what do you mean? Don't forget, 2 problems ago, we found out that 1 kilogram of material corresponds to 9 times 10 to the 16th joules. Okay? So go ahead, take a stab at it. You got it? Yeah, good. So here we go. Ready? How I like to do it, I'm going to go ahead and set up a proportion. Okay? I know that it's 9 times 10 to the 16th joules per kilogram, so I'll put that off on one side. And I need 4.2 times 10 to the 26 joules. So how much material corresponds to that much energy? Okay? And so again, I'll go ahead and cross multiply to get x on one side of the equation and all my numbers on the other. Okay? And so at this point, I go into my handy dandy calculator. Now 10 to the 26th divided by 10 to the 16th, we can subtract the exponents there. So we should get something on the order of 10 to the 10th. Okay? So we plug it in and we get about 0.4 times 10 to the 10th, or if you want to move the decimal point over 1, you get 4.7 times 10 to the 9th kilograms. Okay? Now let's stop and think about that for a second. Okay? That is 4 billion kilograms every second. Right? Every second, the sun converts almost 4 billion kilograms of material into pure energy via this fusion process. Right? Boom, 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 boom. That's, I think I looked it up at some point. I think that's like the pyramid, that's like taking the Pyramid of Giza and converting it into pure energy every second. So now we know how the sun powers itself. We know that in order to do the nuclear fusion process, it must convert material into energy. So the next question, which I think is a good question to ask, how long will the sun be able to sustain this process? The mass of the sun is 2 times 10 to the 30th, and it is converting material at a rate of 4.2 times 10 to the 9th kilograms per second. How long can the sun sustain this process? Yeah, you got it? Yeah, good. I'll go ahead and set up a proportion again. All right? I know that it's 4.2 times 10 to the 9th kilograms in 1 second. So I need to know how long does it take for 2 times 10 to the 30th. I'll rearrange the equation. I'll get x by itself. Okay? And so now again, we see that it's going to be something on the order of 10 to the 21st, just subtracting the exponents, 10 to the 30th, 10 to the 9th, that gives me 10 to the 21st. And so I plug that into my calculator, and I end up with something like 4.7 times 10 to the 20th seconds. Right? Again, that doesn't really have any meaning. I'll go ahead and convert it into years. And you get something that's about 1.5 times 10 to the 12th years. 10 to the 12th trillion. Okay? So let's think about this. We now have a way of estimating how long will the sun be around for, based on how much energy it outputs. Based on our idea about nuclear fusion, we can use those two ideas to get the lifetime of the sun. Now, this number is overestimated. Okay, it's too large. And I'll give you a couple reasons why. Number one, the sun is only about 70% hydrogen. So only about 70% of the material of the sun could participate in this fusion process. So what we could do is basically take this number and multiply by 0.7. Okay? Move the decimal point over by 1. Other ideas. Where the fusion process occurs is in the central part of the star. That is the location, what we call the core. That is the only part of the star that actually undergoes this fusion process. And so in terms of the entire volume of the sun, it's only about 30%, 35% of the entire volume of the sun participates in this fusion process. And so we can multiply this number. I'll do some hand wavy, but we can multiply this number by about 0.3. In addition to that, the core, only about 10% of the hydrogen in the core actually participates. And so you can do another 10. Okay? So at the end of the day, we estimate the sun will actually last about 7 billion years, not 1.5 trillion. Okay. That's basically it. That's as much as we're going to do with the actual equation quantification. Okay. But there is a question here about which one wins. Okay. So do stars with larger gas tanks but are less efficient, do they last longer? Or is it smaller stars that are more fuel efficient? I compare it like a Hummer versus a Prius. Okay? And I'll give this to you without proof, but what we have figured out is that the stellar lifetime goes like the mass to the negative 2.5. What this means is that larger stars, more massive stars, have shorter lifetimes. To give you an idea of that, I have a chart here. Okay? And you see that a star, a run-of-the-mill star, that's roughly the mass of our sun, lasts about 8 billion years. Okay? But if you go 40 times larger, okay, if you're 40 times more massive than our sun, you only last 1 million years, right? 1 million years, that's it. Like, bear in mind, like 60 million years ago, dinosaurs were walking the earth. Okay, so for a star that's 40 solar masses, it has formed and already burned out in the last 1 million years. Like a drop of it's like a blink of an eye in terms of the scale of the universe. But we could go the other way too. Notice that if you go down to half a solar mass, okay, a mass that's a star that is half the mass of our sun can last 56 billion years. These stars haven't even had time to burn out yet. Okay? The universe, by our best models, is about 14 to 15 billion years old. These low mass stars can survive for 50 billion years. Okay? They haven't had time to burn out at all. Cool, huh? Okay, so in summary, okay, what do we start off with? Our ingredient list, one cloud of gas, and that cloud of gas gravitationally collapses, trades off gravitational potential energy for kinetic energy. And because of that, the cloud of gas heats up. Eventually, you get to a high enough temperature that these atoms, these hydrogen atoms in the cloud of gas, begin running into each other fast enough that they fuse. And at that point, that is when you have a star. The point that distinguishes a cloud of gas with a star is, does it have nuclear fusion going on in the core? Once the gravitational collapse is sufficient, and the internal temperature of the star is high enough, the nuclear fusion process can start. Hydrogen atoms smash together and stick. Okay? That is the birth of the star. Okay? Usually that's called ignition, and it is a self-sustaining process. It doesn't turn off until you run out of material, fuel. Okay? So lastly, after the fusion process begins, the star slowly gets less massive. It's slow. Some people use the term burns. That's sort of a chemistry term, but it doesn't. It's a nuclear fusion process. Okay? So the mass of the star slowly decreases over time, and eventually, once it runs out of material, the star burns out. And that's where we'll lead to when we're talking about the birth, life, and death of stars in a couple of videos. So that's all I have for you. Make sure to ask questions, write down any comments, concerns, questions, and give me a chance to respond to those. Hey, thanks for your attention. I'll see you next time.